Hi, my name is Guillermo Cecchi. I work in IBM Research in the laboratory, and I direct the program on computational psychiatry and neuroimaging. And today I'll be talking about ideas that we've been developing around the notion that knowledge exploitation is a complement to explainable AI, which is a topic of interest in this series. What do I mean by that? So we think of explainable AI as the need to understand AI models in the context of current knowledge, right? How to make sense of the AI models in the light of what we know about particular problems. But the conjugate concept of that is the utilization of existing knowledge in AI models, as opposed to this notion that sometimes underlies AI approaches that you can learn everything from data, right? So we don't need to reinvent the wheel. And for lack of a better term, I'll call that exploitable AI. So this will become hopefully more clear as I explain how we go about developing these ideas in the context of work that we have been doing for the past few years, using AI models, in particular natural language processing models, to understand language production in mental health patients. So what we've been doing for some time, like I said, can be captured by the idea of feature engineering. And by that, I mean construction of particular features by us, computer scientists, that may reflect something that is important to be captured, in this case, in language. So a couple of examples is we use voice spectral features derived for instance, speech recognition purposes or something similar to understand the effect of psychoactive drugs in people who that take those drugs, right? So obviously those features might be related to spectral properties of the voice or pauses between words or phonemes, but they are developed, they're engineered as a general tool. And something similar in the case of linguistic analysis. So we use the idea of mapping language onto networks, create graphs out of language, and then use generic features of graph theory in order to try to characterize, for instance, thought disorganization in psychosis. So these are sort of engineered features that we use as very generic ways of understanding, in one case voice, in the other case linguistic production. But in contrast to that, we can think of how to use directly expertise of individuals, clinicians, psychiatrists in this case, their expertise and their insights more structurally, more directly, and including not only that, but also the literature and, for instance, the typical assessments that are performed to study the same problems that I mentioned. So let me be more concrete now and show a couple of examples of what I mean by knowledge engineering. So there are tools that we can use now in NLP, natural language processing, that allow you to consider two pieces of text and measure and give a numerical value to the similarity between them. So how similar they are in terms of content, in terms of structure, and that can give you a number. We call that similarity between the text. And I'm showing here, trying to be cute, an example from lyrics by Bob Dylan that show how you can compare one line to another line in a poem. Using that, we developed the idea of creating the proxy for what is called in psychosis as flight of ideas. So the idea that patients with psychosis jump from one idea to another in a very abrupt way. So we use this semantic coherence, the coherence of the similarity, as a proxy for that. And using that, we were able to show that it's possible to predict conversion to psychosis onset, analyzing interviews of patients who have not had psychosis, but they are at risk. Similarly, we can use automated syntactic parsing of sentences and create syntactic trees that correspond to those sentences and use the complexity of those trees as a proxy for the complexity of the underlying speech patterns and thinking patterns. Conversely, the poverty of those. So the complexity of the syntactic trees is an engineered feature proxy for the poverty of speech. And using that, analyzing descriptions of simple pictures by the participants who were considered cognitively healthy at the moment, we were able to predict onset of psychosis, of Alzheimer's years later. So again, this is another example of the feature engineering that I was talking about. And these features are, in fact, very generic. They're not really specific to the problem that we are studying, to the extent that, in fact, we use both set of features to study both problems, the onset of psychosis and onset of Alzheimer's disease. Now, what I call leveraging is a step in the direction of, like I said, increasing how much and how structured the knowledge that you're using is in creating these AI models. So let me show the example of studies that we've been conducting intended to capture analytically the notion of distortion of the experience of self in psychosis. So this is something that's been very well studied. And this idea that psychosis is both a distortion of the pre-reflective self, the one that compels us to turn our heads when someone calls our name, and the more narrative self, the one that, for instance, we use or we experience when we are talking about the history of our life, for instance. So we have two studies that are intended, like I said, to capture that distortion of self-experience. And in the first one, we studied patients who have already schizophrenia. And we went to the specialists, the experts, and asked them, what, besides, like I said, the engineering features that we sometimes overuse, we asked them, so what type of sentences, what type of phrases you expect in this population that will reflect particular distortions in the self-expression, in the self-experience, in particular around the concept of agency. So that's exactly what we did. We asked what are a good set of sentences that you expect that you have experienced in interviews. And then we had open-ended interviews with this population of patients, open-ended in the sense that they are really free to express themselves. And then literally, what we do is we take those target sentences provided by the experts and scan the free expression in an interview of the patients for similarity to those targets. So based on that, we were able to see that naturally, without prompting, a topic related to the agency, questioning and trying to understand themselves to what extent they have agency, emerge naturally because it's part of their actual experience. So now you can do something that goes one step ahead of that to some extent. And instead of considering the expertise of one or two or a few experts, go to the sources in the literature and consider, for instance, something that is used regularly to assess the same type of condition, questionnaires, right, or inventories in the technical term, that were developed with intention of give a numerical value to different aspects of this distortion of the experience of self. And this is a questionnaire that the patient fills and gives a scale from 1 to 5 for each item. So what we do is exactly the same. We have open-ended interviews, and then we literally rip off those items from the scale-based questionnaire and scan the free expression of patients to see how similar, how close they are to the topics described by the inventories, by the collective knowledge that's been accumulated in this field regarding self-experience. And what is interesting, that's one of the things that we find, is that if you look at the scores, what actually people score, the way they give a number in the questionnaire, it's much higher in the schizophrenia population than in the population that we consider to be at risk, that they didn't have an episode yet, but they're at risk. However, that's what you see in the lower panel as the horizontal axis. And this is how different, how much stronger is the scale for the schizophrenic patients. And that's mostly are to the left of the 0. But then when we look at the free expression, what they express in an open-ended interview, the clinical high-risk population is much more concerned with the same topics, even though they rate themselves much less than the schizophrenia population. So really, this is showing us a clear way of complementing, at the very least, complementing the traditional way of scoring distortion of self-expression, with the advantage that you can do this in a very unconstrained way compared to what you typically do with the inventories. A similar case we can see in our studies of the effect of psychoactive drug intake. So we have done studies on several psychoactive drugs like ecstasy, MDMA, methamphetamine, oxytocin, cocaine, and we started engineering features. Trivially, again, voice features. There is a psychoactive drug. Your nervous system is immediately affected. Your voice is affected. We look at, for instance, spectral properties of the voice, and we combine with some targets that we expect might occur in the discourse of someone who has ingested these drugs, like, for instance, empathy in the case of oxytocin. And sure enough, we can detect the presence, the ingestion of certain drugs. We can differentiate between other drugs. It's all very nice, but it's really difficult to make more progress because these features are, again, they are not specific. They are sort of engineered, like I said. But now we can repeat the same trick that I just showed and actually leverage the knowledge that's been accumulated, in this case, on the problem of cocaine addiction. So we have cocaine addicts, and we have a baseline interview that is open-ended. We just ask them to talk about their relationship to the drug. And then we go to the established questionnaires and inventories, similar to the ones I described before, where you go and say, how often you use, how do you feel about using, etc., and give it a number. Here, we don't have to do that. We have an open-ended interview, but then we use the same approach where you can take the targets, scan the interview, and give a numerical value, and then use that. That's what we did to predict long-term behavior. So actually, we were able to show that we can predict symptoms in particular, for instance, the withdrawal severity of these patients 1 year later using this way of analyzing a baseline interview. And we can do that much better than any other model based on information, clinical information, demographics, neuropsychiatric scores. It's a good number of alternatives. And the free expression of the patient is much more informative than those. Moreover, the models, and this is going back to explainable AI, the models are really interpretable. They are interpretable directly in terms of what we already know. So what you see here in the bottom right is the model that explains withdrawal severity 1 year later, and is based on weights assigned to items in the questionnaires, right? So it really you can relate back directly to what is being known in this field. So a last example that I wanted to mention in particular on language is work that we've been doing in trying to understand, trying to model dialogue in psychotherapy. So what we have here, we were able to get access to a large database of psychotherapy sessions, for which, unfortunately, we don't have outcomes, but that's not an impediment of our model. But we do know that these sessions have been conducted by well-trained therapists. We know that they come from 4 different diagnoses, patients with anxiety, depression, schizophrenia, and suicidality. So what is that we did here? The first thing was to engineer a feature again. And so we went back to the idea that there is one aspect of psychotherapy that seems to be one of the most predictive of good outcomes, and this is the idea of working alliance. And that is the idea that if patients and therapists understand that they're working together, they know they're working towards a common goal, that is a very good predictor of good outcomes. So the way we decided to implement that was to assume or suppose that that alliance was reflected in the mutual information, in the content between a turn of the patient and a turn of the therapist. So we reasoned that if we can create an abstract representation of the turns based on mutual information, that will capture some essential aspects of the good therapy sessions that we have here and allow us to predict, for instance, and this is one of the goals, what the therapist will say after the patient, after any patient's turn. And that's what we get. We get a very good representation that allows us to predict the next turns. Now, the problem with this is, again, as with the other engineering features, is that it's very difficult to make sense in the light of what we already know, right? So we're just assuming that there is a connection between our feature and working alliance, but we cannot go beyond that. So what we are doing now is repeat the same trick that was mentioning, that is leverage information, leverage the knowledge that exists in the field. And in this case, instead of assuming something about the working alliance, what we can do now is map each turn in the dialogue during the session onto the items that correspond to the questionnaire that is typically filled after a session to reflect the degree of working alliance according to the patient, according to the therapist. So the same trick that I just showed, taking inventories that is, and then mapping the normal course of a session onto those, and doing that and assuming that there is a particular way of traversing those aspects of working alliance for the different conditions, modeling that, we were able to show that we can discriminate between the 4 conditions. So in a way, validating that this approach is meaningful, but also predict, again, next turns. So predict the turn of the therapist after several turns between therapist and patient. And for us, this is the foundation of what we're developing now. And that is the possibility of having a therapist recommender or companion for offline analysis of the sessions, and eventually for online support, indication of how things are going during a therapy session. The last specific case that I wanted to mention, and that's moving away from language onto brain imaging. It's a bit more complicated because we don't have the same degree of granularity and knowledge in brain imaging that we have in language. But I think that this example will show that it is possible, and eventually with new tools that are becoming available, we can do more along the same lines, right, of turning engineering into leveraging. So in our group, like many other people, we've been studying brain function for a number of years, and using the basic insight that obviously the brain is a highly interconnected system, and it makes sense to study it as a network. So what we do is we take brain function, we create networks that are representing functional imaging data, and then we apply a very generic approach to describe features of those networks as a simplified way of capturing the complex dynamics of the brain. So, like I said, this is something that is very well studied. For instance, something that we did recently is to show that using that approach, you can detect with just a single visit whether a Huntington's disease patient is degrading, is progressing lower or faster than expected towards the endpoint of this unfortunate disease. And what's is interesting is that this way of looking at the data captures longitudinal information, again, just after a single visit. But again, making a connection between these and anatomy, for instance, is not so obvious, not trivial. So it's not, we are faced with a similar problem of lack of sufficient progress when we just look at engineered features. So as an example of what can be done, what we've been doing more recently is the following. So if we go, actually this goes back a few decades, studies of the dynamic behavior of small ensembles of neurons. That is a very well-studied problem. It has a very clear mathematical representation for the activity of an ensemble of neurons. So then what we do is we take functional brain imaging, in this case, calcium imaging in the zebrafish brain, and we learn how to represent the imaging data, this functional data, as a network of interconnected small ensembles of neurons represented by the way I mentioned. And then to validate that, we predict the future of the future evolution of that data, right? So we use as a validation the prediction of the future. When we take an agnostic state-of-the-art deep learning model and repeat the same thing, that model does much worse. So our neuronal ensemble-based model does much better. But things are never so black and white, because what we see is that if we use our neuronal-based approach to train, or actually pre-train an agnostic deep learning state-of-the-art model, we actually do even better, right? So we see that this is something that is shown in the upper right corner as the accuracy of predicting the future steps after we train or we learn an initial set of points, the evolution over a few seconds. So, what's next? So precisely what we have learned here is that now if we take a state-of-the-art deep learning model and replace the genetic units that are built into them with our neuronal sample units, this is not shown here, but we are getting better results yet than what we have here and we have published. So this is another way of showing that, in this case, a much simpler way of incorporating knowledge can give you an advantage in terms of how good your artificial intelligence models are. So finally, before coming to the conclusions, I want to mention that all what I discussed before is really a very basic research type of approach, but myself being in an industrial laboratory, for us, the applications are very important. And actually, what I just described is extremely relevant for the applications that we are engaged with. And essentially can be described by a change in the way we are doing clinical trials, observational clinical trials, interventional clinical trials. We are actually engaged in 3 of them. One on observing patients with ALS, observing patients and intervening on patients with chronic pain, and observing patients that are at risk of developing psychosis. And the challenge here is that we see those patients every once in a while in the clinic, maybe every 3 months, maybe every 6 months. But then we obtain a huge amount of information on a daily basis from the comfort of their home through questionnaires, text, voice, sensors, watches, phones, everything imaginable. And that creates a huge load of data that needs to be represented, needs to provide a representation of the patient that is consistent, that is self-consistent from day to day, for instance, from set of features to other sets of features, from one type of watch to another type of watch. But at the same time, is connected, is linked to what we know already. And that is, in this case, not only genetic knowledge about the condition, but specifically what we can do in the clinic, right? So the type of information that we can obtain in the clinic has to be incorporated in the representation that we get on the daily basis, and in some cases on an hourly basis, of where the patient is, where the patient is going. So these issues of incorporating and leveraging knowledge are even more critical, because otherwise we have an explosion of data that we really don't know how to deal with. So let me conclude by saying that I think I showed enough support to the idea that it is possible to incorporate existing knowledge directly into AI models, that they have the advantage that provide a degree of explanation and structure to the models that otherwise would not be there, thinking about purely data-driven models. But as I just showed in the previous slide, it can also provide a proxy for clinical assessment, in particular now that we do, in particular after COVID, that we can do so many things remotely and people can do things at home. However, to caution that, let me say that it's obvious, as everyone knows, that we are seeing a phenomenon. We are experiencing a moment of phenomenal expansion of AI capabilities, and that the very concept of explanation may change because of that. I don't have time to belabor that, but one aspect that might be changing is the fact that we might be able to create a standard for interactive or dynamic explanations as opposed to given static explanations, right? So we are used to, like in this case, provide a set of conclusions at the end of the paper, but that may be about to change. And as a source of inspiration, I recommend you to read, if you haven't, a very short piece that was commissioned by Nature in the year 2000 to Ted Chiang. Ted Chiang is the author of the short story in which the movie Arrival was based, in which he speculates about what scientists will do once the science is all done by machines. And with that, I'll finish. Thank you very much.